I'm back after a week of a lot of hard work and honestly some rough weather. But you know what? We're gonna get into the weeds on this one a little bit. So buckle up for some mostly misbehaving robots. This should be pretty interesting.
100? 200?
No, probably like 200-300.
Okay.
It's a big ocean. For a lot of our sponsored projects, as well as commercial projects, military, government, etc., we use an instrument called multi-beam sonar to collect elevation data about the seafloor for loads of different use cases. An example near us is in the Delaware Bay, where there's a large shipping channel that needs to stay properly marked, and it needs to stay deep enough so that the ships that use it can clear the seabed at any given time. So the Army Corps of Engineers actually monitors that using multi-beam sonar. This gives highly accurate depth data across a swath below the boat that's using that instrument. So to use an analogy, if your fish finder on your boat or your depth sounder is a pencil, a multi-beam echo sounder or multi-beam sonar is a paint roller. The data for these sensors needs to be corrected for loads of different things, such as tides or other types of fluctuations in the real-time water level. Also salinity, as well as, most importantly for this video, vessel motion. To get really, really good, evenly spaced data from this sensor, the only option is to keep the motion from the vessel to an absolute minimum. We're not reachable right now.
We're not. Such a shame.
There's just too much going on.
Too much.
Oh my gosh. There are certain things that we can correct for in post-processing, such as some of that vessel motion, but past a certain point, we really can't. And there are actually lots of other things, such as the evenness of the data, that we can't correct for at all. For example, the spacing of the data in the forward-aft direction, or the direction in which the vessel is traveling, is completely dependent on the vessel's speed. So if you're having large fluctuations in the vessel's speed or heading, you're actually going to have irreparable problems with your data's spacing, which is something that we refer to as sounding density. And that's actually a key metric when it comes to evaluating the data products that come out of a project. So to reduce that motion, we'll oftentimes just slap the sonar on a much, much bigger vessel than what it actually takes to run the equipment. The bigger the sea state, the bigger the boat. So for a small port survey, you might see the sensor out on a small boat with a driver and a sonar operator. However, in an offshore survey in worse weather, you will often see these sensors mounted on a large research vessel that takes a 20-person crew to operate and will often have a science party of, say, 10 people. These research vessels are burning loads of diesel and emitting lots of carbon into the atmosphere, and they're costing companies a lot of money. And by the way, this is all to collect data on a sensor that can usually fit in a briefcase. So what's the solution here? In my opinion, it's robots. Wow, the plan for today is come back and do a cleat job a little bit better than this one.
It's very
It goes through. Clearly, some of us are not capable.
that on my
Who did this? You want something that negative on your resume?
You would.
Yeah, do we want to look like the Army Corps though? Oh shit. We would have lost that dock line though. Anyway.
So many complaints.
This is our little Echo boat, which is an autonomous surface vehicle, or an ASV, which is just a fancy term for a robotic boat. And it actually packs the same exact sensor package that you would potentially see on a lot of these offshore larger survey vessels. So now we've got control for the Echo boat, like mission planning, multi-beam control, and now we've got all of like our survey coverage. So the problem is the boat is a little bit of a tin can in weather like this, where the flags are pinned straight out and there's waves and currents. And that causes those motion artifacts that are irreparable, kind of like we were talking about before. The advantage here is that we're able to advance the algorithms of how the boat is controlled far beyond the skills of a human being. So to try and solve this problem, we teamed up with some friends of ours in the Department of Mechanical Engineering at the University of Delaware, who actually specialize in this type of control algorithm development. They helped us develop a path-following control algorithm that sacrifices a little bit of the vehicle's ability to actually follow the path to keep it dead even with heading and vessel speed. Although this doesn't solve all of our problems by any means, it corrects a lot of the issues that we would normally see that are irreparable in post-processing, such as sounding density or data spacing. After a lot of troubleshooting at home and a full week up in New Hampshire with the developers of the software that we use to test everything, Kleio and I took a week in Delaware to test out the controller in some pretty choppy bay conditions.
We're going home.
Okay, maybe not that choppy.
Oh my. Oh my.
Good times only.
Yeah, that's better. And some light ocean swell close to our campus.
Hello, little friend. The line of the day is don't sink the boat.
Oh my god. We're staying at the dock. I think that computer might be donezo after today. Gave us these really good weed guards that block against any type of weeds that might be out in the bay. So just really glad that we had those on while we were out there. That's it.
That's why we're back
that's all I have
at
to say.
11.
Give us a new boat.
Yeah.
The word of the day is calm, or calmness, one of the two. But it's not going to be anything that you said yesterday, because look how yesterday panned out. So that's
Fair.
it. Today's the last day of field testing, and we're going to get some data. That's it.
This is the most aggressive that you'll get, right?
After going through the survey data from these surveys, we are actually able to tell that we improved some of the metrics that we can't correct for after the surveys are done. So what does this all really mean in the big picture? To me, this is the really exciting part. Now, any user of an ASV with a 2-propeller design can improve the efficiency of their survey using just a quick software fix.
No way.
Now, if they decide to use that software update, they can use their ASV in a much rougher set of conditions, or they can downsize the ASV that they're using in the same set of conditions. This is huge for reducing the amount of carbon that is emitted in these surveys that are done for loads of different projects, loads of different applications all over the world.
Today.
And maybe we should have.
Yeah, we honestly should have.
Thank you for watching. Part 2 of the Potomac is coming real soon. If you haven't watched part 1, give it a shot. We just finished the paper for this ASV project, and we submitted it, and we're already back on the Potomac for round 2. So, see you soon.